Hello everyone, welcome back to the channel. So we are at the episode 4 where we are talking about the API first approach in our high level system design series. So let us look uh, at what we have done till now and have a quick recap. So in the previous episode we had a look at how we can clarify requirements, and in this episode we will continue with step 2, or what is the API design, how do we go about designing our APIs in a real world system design challenge. Okay, so let's start with this. And before we dive into the API design and the complexities and the concepts involved around it, I want to share a story that fundamentally changed how the industry thinks about API architecture, right? And the story is about Netflix. So we'll see that how Netflix uh, had this API first design decision in 2008 that enabled them to scale from 1000 requests per second to today they are serving a whopping 10 million plus requests per second. So they have established their streaming dominance here, and that is very much visible with uh, why this architectural choice was very crucial for them, beating Disney Plus and Amazon Prime and other competitors by a decade, I would say. So that's where proper API design can take a business from. So this becomes a very fundamental or foundational pillar in our system design. Okay, so that's why this is very important. So now we'll see that in our paste bin example, right? Our architecture. So we have our architect Alex, and Alex had already completed the step 1, that is clarifying the requirements by asking the 4 layered model of questions. Okay, in that we saw in the previous episode. Now Alex is moving on to the step 2. Okay, that is the API design part of it. So now the business wants this paste bin. Okay, the business wants this paste bin to be called CodeShare. So they are changing the name of the platform and they're calling it CodeShare. And the CodeShare, the business has a legacy system. Okay, today that serves around 100 million requests per day. Okay, it has around 15 clients who are using this API, and the business is seeing that this is breaking constantly, and that is very hard, very tough for the business to manage. So they have come to us as a tech team, Alex and his tech team, to help them out in this situation, and they want us to build a production ready and a scalable and a very developer friendly API which is highly available and which is highly scalable. Correct. So we will start with this approach, and Alex has a few ideas in mind, a few questions that he will ask. So taking the key insight from Netflix, right? Netflix didn't achieve this by accident. Correct. They did not achieve what they did, like they scaled from 1000 requests to 10 million requests, and this was not an accident. They made a strategic architectural decision. Okay, when building a monolithic streaming service versus going for a microservices or API first design approach in mind. So that is the architectural choice that they made from day one. They built for scale, and look at these numbers. Like they went from handling 1000 requests to 10 million requests per second today, right? So they chose API first architecture from day one, and this is what brought them to this scale, right? So why does it matter for our code share project? Okay, because we are facing the exact same decision today, right? Product has given us requirements for a simple payment service, but I know you know that nothing stays simple in that. Nothing stays that simple in production. Okay, our legacy system is already buckling under 100 million requests per day that it's trying to serve today across 15 clients, and we might be having multiple mobile apps or multiple web interfaces, command line tools, okay, ID support and all that. So every change is breaking something. Every feature request turns into a 3 month project, and we have to lean out this model. And so today I'm going to show you the design methodology that will prevent us from repeating these mistakes. We are not just building an API here. We are designing the foundation that will serve us for the next decade. So let's start. So first we'll see what is the difference between the API first versus the traditional development approach. Okay, and this brought a fundamental paradigm shift in the way we develop. And let me show you the difference in how most teams approach API design, right, and how successful companies, top tier companies, they do it. Okay, so here's what 90% of the teams do, and it is exactly what we did in our current system. We start with the database. We design, you know, we first saw what is the database, right? So I'm talking about CodeShare here. At the current state, what we did was we started with the database. Then we design our tables. Okay, we check the ORM entity implementations. Basically, we design our tables. We create the entities. We build a repository layer. Okay, so and then expose whatever the database gives us through REST endpoints. Correct. So what happens is the database and the schema, they decide that what the API consumers get. Okay, what the API consumers get, the database schema and the like the model object, this decides the API layer what it will serve and what the client will get. Correct, and that is where the fault lies. So we have to understand first what the client requirement is, what the clients want. People who are consuming the API, what do they want? Okay, so let's say what will this problem lead to. This will lead to a problem. Let's say we return some API status response which is not really understood, or the client is not expecting that. Okay, the client has to make change. Let's say we change a database at the schema level, we change a field name. At the schema level we change a field name, and the client has to make changes at their end to accommodate this. Okay, field names, internal IDs, ugly timestamps. So our consumer team spend half their time transforming our responses into something useful, and that's what is creating a headache for them. So once we shift from this to this, once we shift from this database first approach to an API first approach, okay, so we start with a completely different question here, right? What do our clients need to be successful? Correct. First we analyze here this. We analyze what are the client requirements, what are the user journeys we are enabling, what platforms need to integrate. Okay, what great developer experience look like. Then we move on to the second part. We design the API contract before writing any code. Okay, so contract before code. What do we mean by contract? I'll show you an example. So we create open API specs. Open API specs. This is nothing but an API contract that we create before writing any code, and we share it with our potential customers. So we are already creating a contract beforehand, and we are saying that okay, our API will serve this and this data, and make sure your systems are ready to consume this. Okay. Then after this, uh, we do some mocks and validation on our API. We clean up field names. We declare public identifiers. Okay, everything that a client needs to build great user experience. We validate all these stuff with the client itself before writing any code. Mark this. Correct. And then notice how we are thinking about visibility levels, expiration times, and short URLs right in contract. Okay, so only after we have validated this contract with real clients, we implement the service layer and design the database schema to support it. So this becomes a reversed approach. Earlier, our data told us what we expose. In the API first approach, client requirements tell us what we need to build. We build a contract based on that. We validate it with our clients, and then based on that, we build the database schema. So this is what an open API contract looks like. I have shared an example for your reference. So this is a YAML file that we built. Okay, so this is the structure. We give the title, version, and all these are the routes that we are going to expose. We are planning to expose. Okay, so this is an API route. Okay, this will be a post method that we will expose, and we are saying that hey, we are exposing this route. We are giving a summary of what it will do. We are clearly mentioning what the request body will be and what the response body will be. Anything other than that will not support and will return respective error responses. Okay, so this is what the first step was, that taking an API first approach for building production grade APIs. I hope you are clear with this, and with this we'll move to the next section, that is now we'll do requirement analysis through API lens. Okay, through the lens of an API first approach, we'll see what how we can do the requirement analysis. So this is something that trips up every team, requirement analysis, right? And product comes to us, in our case, in our CodeShare application, our product or the business team has come to us, and they say that the user should be able to share code snippets. That's what the primary functionality of this system is. Okay, it sounds very simple, right? But it's not that simple, and it involves, like, it brings up many complexities, and we'll tackle these complexities one by one. Okay, uh, in my requirement, I have sorry, in my experience, I have learned that every simple requirement is an iceberg. Okay, so what you see on the surface is might be a 10% of what the actual complexity is. So when you see this question, API first thinking will should trigger this thought that okay, whenever we are asked to share code snippets, is it an anonymous sharing, or are we looking for private sharing, or are we looking for organizational sharing, right? Because in anonymous we don't need any authentication, because we are only supporting public uh, access, and we might need rate limiting, and that to for preventing abuse, right? In the private sharing, yeah, as it's private, we should have some sort of authn or auth or password protected routes, and main thing is that the access should be controlled using expiration policies or stuff like that. When we move to organization sharing, we are looking to provide company only access, like enterprise features, compliance logging, permission inheritance, like using roles and all that stuff. All that stuff comes into picture. So each of these translates to different API operations with different security models, right? Different response formats, different business logic. If we imagine, if we had gone database first here, so we saw this business requirement and we started designing the database of how we will store the code snippets. So we would not be able to serve all these things upfront. We will not be able to design for scale from day one, correct? So yeah, so each of these translates to different API operations with different security models as well, different response formats, different business logic. Okay, and if we would have gone database first, we would have discovered this complexity during implementation phase, and it would hurt us badly then, leading to awkward API changes and breaking client integrations. Okay, so here's the process I want you to understand for every requirement, right? So functional requirements become HTTP operations. Okay, because these are what, so HTTP operations are these translate into our functional requirement. For example, creating a paste. Okay, so this is a functional requirement, and this translates to a post API that we are naming it as API slash v1 slash paste. Okay, so the non-functional requirements become API constraints. Okay, for example, 10 million pastes a day. So 10 million pastes a day, that's a non-functional requirement. Okay, what does this correspond to? This becomes our rate limiting strategy. Similarly, you can see viewing a page, listing my page, deleting page, update page. All these correspond to a separate HTTP route. Okay, so this is the basic. In every system, you can apply this. Functional requirements correspond to or transform to API operations. Non-functional requirements correspond to API constraints. API constraints. Okay. So notice how we are not only thinking about the happy path, correct, but we are also considering error cases and edge cases. Okay. So from day one, keeping all these things in mind really help to build a scalable system or scalable API. Okay. So this was for this section where we do the requirement analysis through an API lens, and we saw that how the functional requirement translate to API operations and how non-functional requirement translates to API constraints. Okay. Next, we see that how do we actually do the resource modeling and the URL design. So, okay, so we saw that okay, we are designing this API slash v1 slash pastes, or we are doing this API slash v1 slash user slash id slash paste. So what is the fundamental or the funda or the logic or the standard practice behind this? So we see that, and so this is a very systematic approach to identifying resources and modeling relationships and designing very intuitive URLs. So this section will cover the difference between RPC style or and RESTful APIs with examples. So we'll see that how it goes. So this is like my favorite part here, resource modeling, and this is where we'll think like senior engineers or architects and not just programmers. And REST, whenever we see talk about REST, we always think about verbs like get, post, put, delete. All these are verbs that correspond to functional actions. So it's basically not only about get, post, put, delete. It's about identifying the resources and their relationships. So let's look at how we do this with the resource discovery process. Okay, so this is the I sort of follow this four step sort of layout process here to do resource discovery, right? So first thing is identify the nouns. Okay, what are the nouns? Not verbs, not verbs. So what do I mean by this? By noun, I mean in our system, what is a noun? It is a paste, it is a user. Let's say we also build comments in future. We have organization, we have collection, we might have all these things. So these become our nouns. Okay. Now we try to see how these relate to the functionality that we are trying to build. Okay, for example, user owns a page, right? Organization has users, paste has comments, paste can have comments. So these relationships become our URL choices, correct? Now we define the hierarchy. Okay, so as the user has space, so in our URL we build it like user slash id, like what is the particular user that we're looking at, and then what are the pastes that come under that particular user. Similarly, orgs slash id slash paste, so under one organization or one company, what are the pastes that its employees are creating. So this is what drives us to design the URL. Okay, then we have a plan for evolution. What if our API grows? Okay, so what if we have to add versioning to our APIs, because let's say v1 was using some architecture or some design pattern to build, and then v2 we updated it, we made it more resilient, we added more features. So that's when we do versioning also. So this is a four-step process for resource discovery. First we identify the nouns, then we find the relationship between those nouns. For example, user owns a paste, then this becomes the hierarchy in the API. So first we'll do users, we'll go to one particular user and we'll see all the pastes under them, and then we'll do versioning. To this API we'll do, let's say we'll add something like API slash v1 slash user slash paste, something like that, to denote that okay, we have versioning in our API, we are supporting, we are backward compatible, and so that the downstream systems who are consuming our API do not have to face this issue. Okay, so Let me show you the difference between RESTful URLs and RPC style URLs, right? So this is an important point that we should know. Okay, so basically, what are RPC style URLs? So these are basically function calls over HTTP. Okay, so so if two systems are connected over HTTP and we are it's basically a function call, and they are not cacheable. They are quite inconsistent and they don't scale. Okay, every new operations needs a new endpoint in RPC style calls. RPC has its own use cases, but we are not going into detail there. And RESTful URLs basically they represent the state. Okay, they represent the state. Sorry, not state. They represent the resources. Okay, basically we are doing post on paste. That means we are trying to create pastes. Okay, they are predictable, they are quite consistent, they're cacheable as well, and they leverage the HTTP semantics. So a developer who understands one endpoint can surely predict that okay, this is how the other endpoints would work in an HTTP RESTful setup. So here's why this matters, right? Because in the industry you see GitHub has thousands of endpoints, but developers can navigate their API intuitively because they follow consistent resource modeling. And uh, another example would be Stripe. So Stripe processes billions of dollars because their URL structure makes it impossible to make mistakes. So that's a very good experience for the consumers of the URL, right? So this was it, that how we design our URLs and how we model the resources, and two types of URL styles that we use in the industry. Now, so now in our CodeShare application, our architect is quite happy. Alex is quite happy, and he has designed the APIs. Now he needs to think about the authorization and the authentication architecture that will safeguard this API that he has built from like unauthorized or unwanted access. So let's talk authentication first. So this is where I've seen most teams either over engineer for day one or under engineer for scale, right? So we need to design for both. So I call this progressive authentication levels because as per the user, we decide that what sort of access should be given based on the user. Okay, so first one is level one. So this supports anonymous users like public pages, and which are rate limited to 10 requests an hour because we don't want to bombard our system with unauthorized requests. And we put a 1 MB size limit on the request, and we put a 24-hour retention time period. So this enables quick sharing without friction, and but we protect our API against abuse as well. In the point level 2, we move on to authenticated user. So we start adding more features. We provide the ability of private pages, and we increase the rate limit to 1,000 requests an hour because these are our authenticated customers. And we also provide them 10 MB size limit because we trust them, and we give them the feature of unlimited retention. So you can see how moving from level 1 to level 2 of the authentication level, we start giving more features. Next is level 3, where we have the enterprise user tier. So in this tier, we start providing organization level features like 10,000 requests per hour, compliance logging, and this is where our revenue comes from mainly. So we provide the best features in this auth level. Correct. So the beauty of this approach is the same API serves all user types. We are not building three different systems, but we are building one system with a progressive capability. Okay. So now which authentication method do we choose? So let me show you the decision metrics that Alex is planning to use here. Okay. So the first authentication method is API keys. So basically there are three that are used in the industry today mostly: API keys, JWT tokens, and OAuth 2. Okay, so API keys are perfect for CLI tools and server to server communication. These are very simple, okay, great for automation, but they are hard to revoke selectively. That is the main issue that I see with API keys. Okay, but overall, for a simple implementation is quite good, and it's used as well. So the next authentication method is JWT tokens. Okay, so by design they are stateless, and these are ideal for mobile and web apps. Okay, they contain the user context and they expire automatically. Okay, but you can't revoke them before expiration, so that is one thing we have to keep in mind. And the primary one and the most used one is, this is the industry standard. This is the OAuth 2 mechanism. So this has granular permissions, and this is quite essential for third party integrations. And it has revocable access, but it's complex. It's little complex to implement at the first go. But yeah, this is the industry standard for the best level of safety that we have. Okay, so the key insight from this system is, don't choose one, right? Design your API to support all three, and different clients might be having different needs, and not all of them need the best industry standard security in the first go. And so different clients have different needs, and a CLI tool ideally shouldn't be forced to implement auth 2. That is quite complex. And a third party integration shouldn't be also limited to API keys. So that's why we should be empathetic and design for all the needs that the end user might have. Okay, so we move on to next section. The authorization and authentication is done. Now we have to see how we version our APIs and how we evolve them. Correct. So let me tell you about the most expensive um, mistake that I have seen happening in API design is improper versioning. Improper versioning, and it hurts us really bad, because due to improper versioning, the consumer teams or our customers end up receiving responses which are not you know not consistent. So an example would be, Twitter spent 8 years migrating from API v 1.1 to v 2.0. Facebook deprecated 2.0 while 4.0 was still in development. So these weren't technical problems, they were strategic failures that caused them bad. So here's how we're going to do it right, and look at this evolution timeline. Okay, so this is how we should evolve our APIs. So the initial release happens with a 1.0 release. Then after the decimal point, whatever number we add points to a non-breaking change. So we go for 1.1, then 1.2. We just do minor changes. Then we go for 2.0. So these are breaking changes, and these are changes which are not backward compliant. So these require a primary version number change. Okay, so this is how our API evolution timeline is. It looks, and now we'll see that what kind of versioning we apply here. So the URL versioning, there is header versioning, and there is a hybrid approach. So when we talk about versioning, we have in while when we talk about URL versioning, these are explicit and visible, right? You can see that API slash v2. So this is easy to cache, and the implementation is simple. But the URL is cluttered. Okay, and the resources are also duplicated. For example, you see here API slash v1 slash paste, API slash v2 slash paste. So only the version is different, the other resources are same. And then another versioning strategy is header versioning. So what we do is, instead of putting the version in the URL itself, we put the version in the header of the request, v1 plus json, v2 plus json, something like that. So this results in clean URL, and this supports granular versioning also, rest compliant. It is rest compliant, but from client's perspective it becomes little complexity. The readability of the API, that is not quite good. So only header versioning alone becomes little challenging. So what serves the best is a hybrid approach where we get the best of both worlds. So what we do is major plus minor versions here, correct? So we 1.2 for minor, basically whenever we are providing a minor release, minor upgrade to the API, we add it to the header, and whenever we are releasing a major upgrade to the API, this red one, we add it to the URL. So this solves the problem. Okay, so we saw the evolution timeline, and now we let's see the comparison between the non-breaking changes and the breaking changes. Okay, so understanding the difference between breaking and non-breaking changes is very critical. So non-breaking changes are, safe changes like adding optional fields, new response fields, and anything which does not impact the existing clients, and they can work without modifications. Okay, so as we saw, the decimal point number upgrades is generally used for non-breaking changes. The breaking change requires a new version. So basically, any change that involves the existing client will break and require code changes. In those scenarios, we go for a main version number upgrade. Okay. So here's the basic rule basically. So if you are not sure whether a change is breaking, assume it is. So be on the safe side. Assume it is a breaking change, and it is better to be conservative and maintain backward compatibility than to break client integrations, right? So remember that APIs are promises to your clients, okay, or contracts that we've already signed. So when we break those promises, we break the trust, and in API economy, trust is everything. So that was about versioning. Now we'll move on to error handling and HTTP status code strategy. Okay, so let's talk about something that most teams do poorly: error handling. Okay, so we have seen APIs where every error status even returns 200 OK status, and that is not very trustworthy. So also we have seen APIs that return something went wrong for every error, and this is very something went wrong, and this is very frustrating to see such a response for every type of error that occurs. Okay, so handling is where you can really differentiate your API. A well designed error response turns developer frustration into productivity, so that's a very important thing. And here's the decision framework that you can use for HTTP status code. Every request would go through this flow. You say that is the user authenticated or not. If not, you say 401 unauthorized. Okay, similarly, all these questions you can ask, and this can lead to a decision flow, and based on that we can configure our error responses, correct? So this is what can help us. This systematic approach ensures consistency across the API. Developers can predict how the API behaves, and even for endpoints that they have never used. Okay, so here's an example between a poor error response and a rich error response. So the problems with the poor one is the status code is wrong, and we have an unhelpful message which does not tell us anything, no actionable information, correct? And in a proper rich error response, we have a proper status code which gives us that okay, we have an unprocessable entity here, the validation failed. And what is the validation failure? Basically the content exceeds the size limit, and on which field the error happened. It also points us to the relevant documentation. So this becomes this API, even if it is an error, it turns into a productivity boom for the developer, and in one go they can fix this. So this is very very helpful, and it can help us improve our API credibility. So we'll move on to the next section, that is performance and caching consideration and architecture for our API. Okay, so let's talk about performance, right? So most teams think about performance as an optimization problem. We'll make it fast later, but performance need to be designed into our APIs from day one. Okay, so here's a multi-layer caching strategy we are going to implement. So Alex, our architect has come up with this caching strategy that he's going to suggest for CodeShare. Okay, so layer one is browser caching, HTTP headers that let clients cache responses locally. So this caching happens on the client end in their browser or their whatever device they are using, and this is controlled using HTTP headers, or e tag headers. E tag validation is what controls the browser cache or client side caching. Layer 2 is CDN caching, which happens on global edge servers that serve content from the nearest location. This is the CDN caching. The third one is the application cache, right? So basically we have Redis instances or memcached attached to our application server. So these act as application cache and cache the computed results and results of database queries as well. So this caching happens at the app level layer or our server layer. This is the client one, and this is the CDN one, and the fourth one is the database caching. So basically what we do is we might query the result caching. If we see the system observes that a query is being executed multiple times, we can easily go for database level caching. Okay, we can also go for connection pooling, query optimization. We can pin indexes we are frequently accessed, and all this will increase the database response times. Okay, so we'll look at caching later in our series, as we have a like a focused episode coming up on caching. So we'll discuss all these caching layers in detail there. Okay, so each layer serves a different purpose basically, but together they can create a system that can handle massive scale with very low latency. So here's a very good example of a performance first thinking, that is pagination. So offset pagination seems simple, but it is a performance disaster, right? To get to page 500, the database has to scan and skip, you know, how many 10,000 records. So performance degrades linearly with the offset sites. So that is very bad. Cursor pagination uses the database's natural ordering. The database seeks directly to the cursor position. Performance is consistent whether you are on page 1 or page 1000. So that's a very natural way of pagination, and it's followed across in good teams across the industries. So this is the difference between an API that works in development and an API that works at Netflix scale, let's say. And so basically, Alex has done a very good job in designing the API, and I think he has achieved a very good API state now. And he has designed for the scale that he wanted for CodeShare, right? That the business asked him, that 10 million requests a day, and he did the right thing. Okay. One very important feature is real-time feature integration strategy, right? So what is this? So modern applications need real-time features, but real-time doesn't mean the same thing for every use case. So let me show you how to choose the right technology. So REST polling. So basically I have segregated the real-time selection matrix into three parts. So we can select REST polling, we can select server sent events, or we can select WebSockets. So REST polling is simple but inefficient, so good for basic status checks and low frequency updates, right? Server sent events are perfect for server to client notifications, for example live feeds, status updates, push notifications, etc. Okay, these are unidirectional, and they also there are various browser connection limits when we implement this. Next is a WebSocket. So the key insight is that we don't choose one technology for everything, and WebSockets enable full duplex, like bi-directional communication. So it's real time and the mostly used for chat applications or live editing. Okay, real time collaborative tools, let's say collaborative coding IDs and all that. So where a bi-directional communication is very required. Okay, so the key insight in this section is we don't choose one technology for everything, and based on the use case, which let's say in CodeShare later at some point we add collaborative coding as well, like collaborative editing of the page. Okay, then we should go for WebSocket mode of communication. Other than that, for today, whatever the APIs is we have, Alex thinks that okay, REST polling is what will suffice our requirements because we are designing the APIs, and we have CRUD functionality, basic CRUD functionality today. Okay, so look at our hybrid approach. Like this example can help you understand it. So we use REST for the initial data load, correct? Because it is very reliable and cacheable. Okay. We use WebSocket for real-time updates because it is fast and bidirectional. Okay. We have automatic conflict resolutions when versions get out of sync. So based on whatever the use case is, initial data loading of the system, REST, basic REST endpoint suffice. We go for that. Collaborative coding and editing, we need bidirectional connectivity. We go for WebSockets, correct? So you see the difference in API response structure and all that, right? So in the WebSocket, we have a type and the data, and for conflict resolution use cases, okay, uh, where the various versions of the API go out of sync, then we go for conflict resolution. So REST is best for reliability, and WebSocket is for speed and automatic fallback and conflict resolution. So finally, Alex is happy now that he has designed the CodeShare API, and he did a pretty good job for his team designing the CodeShare API and bringing it to production readiness and closing it. So let's talk about what separates a demo API from a production ready system that can serve millions, right? So security isn't optional. HTTPS enforcement, proper authentication, input validation, rate limiting, these aren't nice to have, but they are core requirement of this of any API design that we're doing. Okay. Now the next one is performance, right? Performance needs monitoring from day one. It needs caring, and we need to provide proper thought process to it, thinking in terms of caching strategy, CDN integration, database optimization. You can't optimize what you can't measure, so we have to monitor. The third one is documentation and developer experience. Documentation is part of the product, okay, that it's not optional. And complete open API specs, interactive documentation, code examples, SDKs. Your API is only as good as your documentation, so I can't stress enough on the fact that how important documentation is for a production ready API. Okay. And similarly, we have monitoring and observability that we saw, proper response and request logging, metrics collection, okay, health check endpoints, distributed tracing setup with correlation IDs and stuff. We should be very vigilant with error handling and reliability, as we saw that a proper error response can really be helpful to the developer. And API governance and evaluation, where we saw how we could implement a proper versioning strategy and how we can release breaking and non-breaking changes. Okay, so let me leave you with four principles uh, that can guide every decision in terms of API design. So first one is contract first development. Design the API before implementation, right? Use API specifications. The way we did in CodeShare, we build the contract and then we uh, got into coding. Second is client-centric design. Think from a developer's perspective, optimize for common use cases, and make APIs discoverable and delightful. Third one is evolutionary architecture. So plan for evolution or change from day one. Version thoughtfully, and try to always maintain backward compatibility. Okay. The fourth one is production ready thinking. Security is not optional, performance is a feature, and monitoring is essential. That is the core. And documentation, as I said, is a part of the product. Okay. So with this, I leave you with the core philosophy that great APIs are designed outside in, basically thinking what the client needs first and not inside out. Okay. This architectural decision can impact the scalability, maintainability, and the developer adoption of your API. So with this, we come to the end of the episode here, and I would really like to thank you for watching this episode. And if you have made it till the end, congratulations. I hope that I have added value and have utilized your time properly with this video. And in the next video, we'll continue with our high level system design playlist. And thank you a lot for watching. Please do provide your feedback so that I can improve even further.